Hey everyone, and welcome to The Explainer. Today we're diving into something that is quite literally the hidden pulse of the internet. We're talking about the very protocol that, when it's configured incorrectly, has historically taken down massive platforms like Facebook for hours at a time. We're going to explore the incredibly dynamic life cycle of internet routing. If you've ever found yourself wondering how data actually physically finds its way across the chaotic, ever-changing web of global infrastructure, well, you're absolutely in the right place. We're going to break down the complex mechanics behind all this, relying on the exact source documentation that engineers use to build the system. So let's kick things off with a pretty massive question. When you interact with cloud data, whether you're streaming a huge 4K video, pulling data from some remote server, or honestly just sending a simple email, how does that data practically navigate the massive, ever-changing internet? Because actually, the internet isn't just one giant pipe. It's this dizzying, tangled web of millions of intersecting networks, and it's constantly dealing with hardware failures, brand new connections, and sudden traffic jams. So how do the routers sitting at all these intersections know the absolute best path to get your data where it needs to go without just hitting a dead end? Well, the secret sauce here is our core topic for today, BGP Path Advertisement. You can kind of think of BGP, the Border Gateway Protocol, as the internet's postal service. Path advertisement is basically the essential method these BGP routers use to share their local maps with one another. When a router learns a new route, it doesn't just keep it a secret, right? It advertises that route out to its BGP peers. And by constantly exchanging this information, routers are able to collectively build this massive, highly accurate, and totally up-to-date global view of the internet's routing tables. Okay, let's dive into this. To really wrap our heads around how this works, we're going to follow a logical life cycle. The internet's routing brain, learning and sharing routes, inside the BGP update, managing route life cycles, and then finally, scaling massive networks.
Starting off with Section 1, the internet's routing brain.
To truly appreciate this brain, we've got to talk about scale. Global networks are definitely not static. I mean, you've got cables getting sliced by construction crews. You literally have curious sharks occasionally biting underwater fiber optics. Yes, that's a real thing. Routers lose power, and the physical landscape is just shifting every single minute. So to manage all that elasticity, BGP routers are locked in this continuous real-time conversation. They have to continuously advertise learned routes to their peers. It's this constant chatter that ensures if a physical pathway goes down in Tokyo, a router over in New York knows about it almost instantly and can just seamlessly reroute your traffic.
Moving right along to Section 2, learning and sharing routes.
So how does a specific route actually get born? Well, the operational flow is incredibly structured. Step 1 is route learning. A router has to discover a path first, and it gets this either from its peers or from a static configuration put in by a human engineer. Then Step 2, the BGP Update message. The router actively packages up this new knowledge and fires it off to inform everyone else on the network. And finally, Step 3 is route refresh. Because routers don't just set it and forget it, they periodically re-advertise these routes just to make sure the whole global map remains perfectly synchronized and up to date.
All right, Section 3, inside the BGP update.
Now, what's really interesting here is that when an update message gets fired off across the network, it carries a vital identification badge made up of some very specific attributes. Think of these like built-in safety checks and turn-by-turn directions. First up is the AS path. This records the exact sequence of networks, or autonomous systems, that the route has already traveled through. If a router ever sees its own AS number listed in that path, boom, it instantly drops the route, so data doesn't just loop in endless circles. Next, we have the next hop address. This is the precise IP address of the very next router in line. And finally, the prefix length. This dictates the size of the network prefix in bits, which is basically the fundamental math used to select the best route.
Which brings us to Section 4, managing route life cycles.
Now, up to this point, this might sound like some totally automated free-for-all, where routers are just blindly sharing everything with everyone. But in reality, human engineers are very much acting as the traffic cops here. Using strict advertisement policies, administrators tightly control exactly which routes are advertised and, crucially, to whom they're advertised. I mean, you certainly wouldn't want your private internal company traffic taking a weird detour through a competitor's network, right? So admins implement these rules using complex filters and route maps to ensure that all this automated sharing perfectly aligns with their own business and security goals.
And that brings us to two really vital management tactics engineers use to maintain order. First, we have route aggregation. Just think about the sheer size of the internet for a second. If a router had to memorize every single individual IP address, its memory would max out instantly. No way it could handle that. Route aggregation solves this by summarizing multiple distinct routes into one broad route, which dramatically shrinks the BGP routing table size. But on the flip side, what happens when a link suddenly fails? Well, that's where withdrawal of routes comes in. A router will actively and immediately prune a dead link by sending an update with a withdrawn routes field. This instantly pulls that invalid route from everyone's maps. So you're shrinking the map to save space and rapidly pruning the dead ends to stay accurate.
Let's move to our final piece, Section 5, Scaling Massive Networks.
As we all know, the internet is growing exponentially. Standard BGP rules, they work flawlessly for medium-sized setups, but at a truly massive scale, the architecture would simply collapse under its own weight, for sure. So, the source outlines two distinct structural solutions for this. First, route reflectors. Instead of every single router having to connect to every single other router, which is literally impossible to scale, reflectors act as a sort of central megaphone to efficiently propagate updates across the entire system. Second, we have confederations. This is where you take one massively unwieldy network and just completely shatter it into smaller, much more easily managed administrative units. Both of these tactics keep the processing overhead low while keeping the communication lines wide open.
So, the absolute crucial takeaway is this. Everything we've just talked about, the continuous update messages, the AS path loop prevention, the route maps, the reflectors, all of these highly complex rules and systems ultimately serve one single unified purpose. BGP enables the selection of the best path to a destination network. Out of thousands and thousands of possible ways for your data to cross the globe, BGP calculates and selects the absolute optimal one, and it does it in milliseconds.
To quote our source material directly here, it plays a crucial role in ensuring efficient and reliable routing on the internet. And you know, that reliability is the absolute bedrock of modern computing. Without the BGP Path Advertisement lifecycle working in the background, ensuring every router intimately knows the landscape, all those seamless cloud services we rely on every single day, they simply could not exist. Which leaves us with this final thought. We rely on the internet functioning as a single, coherent entity, but without BGP's constant automated updates, without this endless, invisible conversation between routers sharing their maps and pruning their dead links, how quickly would the internet's map become just a complete maze of dead ends? It is a brilliantly fragile system entirely held together by continuous communication. Thank you so much for joining me on this explainer. Keep learning, keep exploring, and until next time, stay focused.